It's not traveling 1624 meters from here to there, because it's much less time. So let's just try to figure out that distance. So the distance traveled from the muon's point of view, well, it's still under the muon frame, is going to be the speed, 0.997528, times 3 times 10 to the 8th. That's the speed, and then the time was 0.381 times 10 to the -6th seconds. So how far do the muons think Denver is traveling towards it? From the moment Echo Lake passes the muons, or at the moment the elevation of Echo Lake passes the muons to Denver getting to the muons?
I got 114.0.
114.0
Yes.
meters. So there's a very clear difference in the distance that was traveled. What is the ratio of the distance the scientists say to the distance the muons say? We've got a little bit of rounding difference, because before we had 14.231 and got 0.243. So there seems to be this length contraction going on. So far we have a formula of time dilation. That T is equal to gamma TP. And now we have something known as length contraction. All right, so first we have to figure out what's the proper length. Again, the proper means that it's at rest. So again, you use triple beam balance, you're finding the rest mass, because the balance is at rest relative to the mass and relative to you. Which of those numbers, the 1624 or the 114 meters, is the rest distance, the rest length of Echo Lake to Denver? Another way to ask yourself, from the scientist's point of view, you got Denver, you got Echo Lake. You got a distance there. Are Denver and Echo Lake at rest relative to the scientists?
Yeah.
All right, from the muon's point of view, you got Denver and Echo Lake. Are they at rest relative to the muon?
No.
So the proper length is what the scientists see. So you have this proper length is equal to gamma times the length. Now, despite the fact that proper has gotten shifted over to the left-hand side, in both cases, the right-hand side, the TP here and the L here are from the muon's point of view. The T and the LP are from the scientist's point of view. Questions to hear? So we've now established that the time that we generally experience is not the time that necessarily everything experiences, and the length or the distance from one place to another is not necessarily the same for everyone. Let's take it one step further. If I have an 11-foot car and a 10-foot garage, how fast does the car need to travel in order to fit completely inside the garage? Or how would you even approach it? Assume that both of those lengths are proper lengths. All right, so first off, I'm gonna have some ratio here of one length to another. I know gamma has to be bigger than 1, or it can't be less than 1. So what's gamma gonna be? So from here, I know gamma, just from the two numbers, it's either gonna be 11/10 or 10/11. Only one of them makes any physical sense there. So gamma's gonna be 1.1, which is gonna be 1 over the square root of 1 minus beta squared. So, I guess square both sides. So we got 1.1 squared is equal to 1 over 1 minus beta squared. Then 1 minus beta squared is equal to 1 over 1.1 squared, which is 1.21. Beta squared is equal to, let's see, add that, subtract that, says 1 minus 1 over 1.21. So beta is the square root of 1 minus 1 over 1.21, which is
0.4166.
units?
Is it a ratio? So nothing?
Correct. All right. So if that car, so I'm standing by the garage, watching this car coming at me. If that car is going 0.4166 times the speed of light, I can get it to just barely fit inside. What's the problem with that? I mean, yes, that what I just said is true. What's it look like from the car's point of view?
Everything is slow, I guess. If something's really going really fast, then wouldn't like everything around it be like?
I was thinking in terms of, I was simplifying my universe. So just car and garage. If I'm standing by the garage, car, garage, and me. I'm standing by the garage, my hand's on it, I'm going the same speed as the garage, so from my point of view, the garage is at rest. Car's coming at it at 0.4116 times the speed of light. The length of the car is 10 meters, or 10 feet. If I were in the car, so again, just car, garage, and me. So you're in the car, what are you seeing?
Would the garage be 11 feet?
Nope. What's moving from your point of view?
The garage.
All right, so if the car is moving, is its size bigger or smaller? From the garage's point of view, the car shrank. From the car's point of view,
The garage also shrinks?
yeah. So from one point of view, the car fits in completely. From the other point of view, it doesn't. There seems to be an issue there. So let's deal with it. All right, questions before we, last time, did I do the twin paradox? All right, I'm going to jump back just a little bit, do the twin paradox, and then I'm going to jump back to this problem here. Questions before I jump back?
So when we say the car shrinks from the garage's point of view, are we talking like all dimensions? Or,
The dimension along the direction of the speed.
so we're talking about how long the garage is?
Yes.
How deep it is?
Yes.
The car is,
Yes. The width of the car doesn't change. I'm assuming that I'm sort of basically right there in the garage. I'm looking as the car's coming straight onto me. If I'm off to the side watching the car, then that's a different situation. Let's keep it simple for now. All right. So we seem to have this bizarre little conflict right here, depending upon the point of view, and we have this idea of time is not the same for everyone. So let's take a look at two scenarios. Earth, distant planet, rocket zipping past Earth, going to the planet, coming back. So this is from Earth's point of view. Meanwhile, from the rocket's point of view, planet X, Earth, that planet is going, try that one again. Cancel. No. From the rocket's point of view, the Earth and the planet are zipping out and then coming back. Probably should have drawn that. I'm going to draw that differently. Basically, the spirit of what I just wrote, absolutely still good. So from the rocket's point of view, planet X zips to them and then back, and Earth zips away and then comes back. In this scenario here, the rocket's traveling at, let's just say 0.99 times the speed of light, so beta is 0.99. Let's figure out how much time will pass, what is going to be the time difference. So if that's beta, gamma is 1 over the square root of 1 minus 0.99 squared. So I want to be kind enough. So if the rocket ship, from the Earth's point of view, is gone for a year, then if there were identical twins, sorry, flip that around, start over. Let's say there's identical twins, identical twin on the rocket ship, identical twin left behind. From the twin on the rocket ship's point of view, that person is aged a year. So for the person on Earth, that person is aged 7.089 years. The identical twins are no longer the same age by a considerable amount. There's now more than a 6-year difference between the two. So the rocket was traveling near the speed of light. They did not age as rapidly as the people who stayed behind on Earth. However, from point of view number 2, the rocket is still and the people on Earth are traveling. So from this point of view, it seems like the person on Earth, the change in time for Earth would be 1 year, and the people on the rocket ship would be 7.089 years. So we have these two different situations here, different points of view, but only one of them can be true. When the rocket ship gets back to Earth, only one of these actually can happen. It's not like you can be two different ages at the same time. And this is the case right here. The top case is what would happen. So the question is, why doesn't it happen down here? What is physically different between the people on the rocket and the people on Earth? Besides, one's in a rocket ship, one's not.
the Earth is 7.089 years, and the rocket is 1? Or
Yep.
Okay.
So that's Earth's point of view, and this is the rocket's point of view. So for the rockets, what is wrong with this scenario down here? Or probably better, more specifically, imagine yourself on the rocket, imagine yourself on Earth. What is different about your experiences?
This is for the first example.
The first example is the rocket's moving, goes to the other planet, comes back.
So then that's what we're trying to find the difference in.
Yeah.
Okay.
So there's a physical difference between what's happening in Earth's point of view and the rocket's point of view. And it deals with what people experience.
Is it time?
Well, time will definitely be different between the two, but more physical than time passing.
Gravity.
You could probably get there from gravity, but probably not the easiest way.
I mean, is it that they're the ones moving relative to almost everything else?
The movement is not the issue.
Speed.
All right, you're in a car, you're driving at 60 miles per hour, you pass by a hitchhiker on the side of the road. So from your point of view, so once you pass the hitchhiker is moving that way at 60 miles per hour, you're going that way at 60 miles per hour. You realize that you would like to pick up the hitchhiker. What do?
You go back.
Before you go back?
You,
Slow down.
Ah. So from your point of view, the hitchhiker slows down. What do you feel as you slow down? Make it more extreme. You slam on your brakes.
Well, your own momentum? Or your inertia?
Yeah, I was going for inertia there. So what do you feel? If you slammed on your brakes, what would happen to you?
Jerk forward.
Yeah, okay. Now, the hitchhiker, what do they experience?
Nothing. Well,
Yeah. I mean, so when you slam on the brakes, there's a physical difference between what you experience and what the hitchhiker experiences. Even though from both points of view are valid, you can look at that, you can just look at the hitchhiker in your rear view mirror and you see they're zipping away from you and then they brake very quickly from your point of view. But they don't actually physically feel that braking. That's the difference here, because the people on Earth don't actually feel the turnaround, whereas on the rocket, you will feel that turnaround. So, that is the difference between the two. Special relativity is what they sometimes refer to as inertial reference frames or non-accelerating frames. And acceleration sort of collapses one of the possibilities. Now, before the rocket ship turns around, in this scenario up here, the people on Earth have aged more than the people in the rocket. In this scenario here, again, this is before the turnaround, the people in the rocket have aged more than the people on Earth. And it seems incredibly contradictory. But that seems to be the way special relativity is telling us, what special relativity tells us. Okay. Now, another thought experiment.
Wait, so which point of view actually happens in real life?
If the rocket turned around and came back, then this is the correct situation here.
So what exactly makes the inertial reference frame? What decides that? Or makes it?
Why is this true and not that? What is it
Yeah.
about the acceleration?
Is like everything else somehow still or realer or something?
That gets into general relativity. General relativity deals with the accelerating frames, and yeah, I can't really answer the question about why. Yeah, I can do a song and dance, but ultimately, it just seems to be the way it is. Again, general relativity, capable of that. Special relativity, on the other hand, much simpler. Other questions? All right, thought experiment. I got a train cruising along the track here. On top of this train is Lou. Over here is formerly conjoined twin Sue. Sue and Lou show up enough a lot of times. That dotted line represents the closest distance the track is to Sue. Inside the train is a detector, and I have two things that will emit light. When the train, so detector is smack dab in the middle,